We're here. All right, let's talk about quantum mechanics. And this is, I'm spend a few minutes on it. Uh, if you get further in your chemistry career, you will take an entire course on quantum mechanics at some point, maybe more than one course. So I'm just going to graze the surface. All right. Um, where did we leave off? Okay, yeah. So we said electrons can be waves or particles, and it depended on how you measured them. What this kind of led us to um, is this idea called the Heisenberg uncertainty principle. Okay, so, and I've hinted at this before, like when you're trying to measure where um, an electron is, you have to give it energy, and then doing that, you move the electron. So it's really difficult to know what's going on. So the uncertainty principle is telling us uh, that it's impossible to know simultaneously both the momentum and position of a particle uh, with certainty. So it just means you can't precisely know momentum and position at the same time. And Heisenberg came up with an equation, excuse me, to define this. This is momentum, and this is position, right? The delta x and delta p just mean it's the change in or the uncertainty in the position of the momentum. Momentum has a mass component, which is going to be constant because the particle's mass doesn't change, and velocity. Okay, so we can think of this as you can't know the position or the velocity with certainty. And if we think about this, this is saying, okay, that's Planck's constant. 4 pi is just a number, so this whole side is a constant. Okay, if you want to know the position precisely, okay, get this to be very, very small, then this number ends up being very large because they have to be equal to a constant. Okay. Um, and this was a problem because they're saying, okay, we want to define an orbit for an electron. We have to know where the electron is. We have to know what its energy is. We have to be able to predict where it's going. Okay. Energy and momentum are intimately related. Okay. So essentially what Heisenberg has said, well, you can't know energy and position at the same time. And that kind of screwed us up because if you want to define an orbit, you have to know energy and position at the same time. Okay. And this was a problem. So enter a guy by the name of Erwin Schrödinger. Here's Schrödinger. Schrödinger's famous for his Schrödinger's equation. This is Schrödinger's equation. We're not going to do anything with it. I just show it here so that we have it. And he came up with this in 1926. He was an Austrian physicist. And this equation describes the behavior and energies of some atomic particles, or mainly electrons, is what we're concerned with. And what Heisenberg did to come up with this equation was he started to employ statistics. Okay, and in doing that, what he really decided was saying that, okay, we don't care so much about exactly where the electron is. What we care about is what the energy is, right? How can we define what the energy of the electron is? Okay, and if we can define the energy with precision, then we can, and don't care about the position, we can just kind of say, okay, well, the electron should be somewhere over there. Okay, and if we don't care about it, then this is what the energy is. And so this is what we've done. Okay, so he essentially used statistics to get an end run around the Heisenberg uncertainty principle. And this was the birth of the field of science known as quantum mechanics. Okay, so quantum mechanics is this hybrid field that encompasses math and physics and chemistry, uh, and its whole purpose is to describe the odd behavior of electrons. Okay, um, math here being calculus, differential equations, statistics, all of this stuff falls into play as we're looking at it. Okay, so what Schrodinger has done for us is define something called a wave function. Okay, if we go back, this is the wave function. Okay, the Greek letter psi. okay, is the wave function. Okay, the wave function gives us information about a particular energy level for the electron. Okay, it basically describes the electron. Okay, but what's great about this is if you take the wave function and you square it, you get the probability, or the probability of finding an electron there. Okay, so remember, we're not going to actually go looking for the electron, but if we can kind of say where there's a high likelihood of finding an electron, it makes sense. So, and if we plot psi squared versus the distance from the nucleus, so this would be the nucleus, okay, what we'll see is the probability is high close to the nucleus, and it peters out the farther away we go. Okay, something to pay attention to here is this does not actually ever hit 0. Okay, it gets very, very close to 0, but doesn't actually go all the way to 0. Okay, it's telling us that even if you're miles and miles and miles, I should say kilometers and kilometers and kilometers away from the nucleus, there's still a slim non-zero chance of finding an electron there. Okay, and that makes sense. Okay, to go one step further than this, we have to remember that atoms aren't linear lines, right? We've decided atoms are spherical, right? So if we convert our probability into a radial probability, okay, and by radial probability, what we're doing is we're taking into account the volume of the sphere, okay? The volume of the sphere is really small in the center, so it's less likely to be in the center because there's less volume there. And the bigger you get out, the more volume there is, the more probability there is up to a point, and then it starts petering out the same way we saw the linear probability do. Now, what we've seen and what has been shown in this when we look at radial probability is that for hydrogen, there's a max probability here around 50 picometers. And this is the same distance from the nucleus that had been predicted, that Bohr had shown and all this stuff. And so this kind of uh, woke up everybody and said, hey, now things are kind of almost making sense. I say kind of almost making sense because I don't really believe anyone understands completely quantum mechanics everywhere, but you know, we'll figure that out. Anyway, once we've got this, now we can start to think about energies of electrons. Okay, and this is where we're headed, energies of electrons. And so what quantum mechanics has done for us is taken this idea of Bohr's model of orbits, of exact circular paths around the nucleus where the electrons are, and turned it into this idea of an orbital. And this orbital is named in it's named orbital as a homage to Bohr in his orbit, because it's not really an orbit, but it's kind of like an orbit, and that's where we came from. Okay, the orbital is just a volume of space that has a high likelihood of finding an electron. Okay, so if we look at it, our wave function, our psi, this is now a mathematical expression that uh, defines the properties of the orbital. Okay, and what that does is that gives us what the orbital, what that volume of space is like, and it defines that volume of space. Okay, it defines things like the size, the energy, the shape, how it's oriented in three-dimensional space, and it defines something called the electron density. Right, the electron density is how likely we are to find an electron in that particular volume of space. Okay, so Schrodinger did an end run around Heisenberg uncertainty principle by using statistics. We now have something called quantum mechanics that defines a wave function. Wave function defines an orbital and defines where we're likely to find electrons. Okay, this idea of an orbital is going to come up over and over again, so I want to make sure that we get that. It's nothing, I mean, it's simple and complicated at the same time. So I'm sorry about that. That's just how this is. But the orbital is just a volume of space where we're likely to find an electron. Okay. In a little bit here, we'll talk more about what the orbitals look like and that kind of stuff and energies and all that. But right now, we just want to define what that orbital is. Okay. I think that's it for this one, and I'll catch you later.